Grounding electrical services provides several important benefits. Firstly, grounding provides safety by preventing against electrical shocks by providing a low impedance path for fault currents to safely flow back to the source, which is the transformer. By providing a preferential path for fault current, grounding helps prevent voltage spikes that can damage equipment and cause fires. Secondly, grounding assists with voltage regulation by establishing a stable reference potential for voltage regulation. By connecting the electrical system to the earth, a common reference potential is provided, helping stabilize voltages and prevent fluctuations. Thirdly, grounding provides surge protection. While grounding alone does not directly protect against lightning strikes, it plays a role in surge protection by providing a path for excess current to dissipate. When lightning strikes a grounded structure, the current travels through the grounding system and into the earth, minimizing damage to the electrical system and appliances. Fourthly, grounding ensures code compliance. Electrical codes require grounding to ensure the safety and proper operation of electrical systems. Grounding is an essential component of any electrical installation to meet safety standards and prevent hazards. Ground fault current does indeed return to the source, which is the transformer, via the grounded conductor, usually the neutral wire and the grounding electrode system. The circuit breaker trips when the current flowing through the grounded conductor exceeds its rated value, indicating a fault in the system. While grounding does not completely protect against lightning strikes, it is an important safety measure that provides several benefits, including ensuring proper operation of electrical systems and appliances, protecting against electrical shocks and fire hazards, contributing to surge protection by providing a path for excess current to dissipate, and meeting electrical code requirements for safety and reliability. The purpose of grounding in electrical systems is multifaceted, primarily revolving around safety and the reliable operation of electrical equipment. Grounding creates a low impedance path for fault current to return to the source, typically a transformer, allowing overcurrent protection devices like circuit breakers to quickly trip and clear the fault. This rapid clearing minimizes the duration of potentially dangerous voltage on exposed conductive surfaces, reducing the risk of electric shock. Grounding also helps to stabilize voltage levels within the electrical system. By connecting the system to earth, a common reference point is established, which helps to prevent voltage fluctuations and imbalances. These fluctuations can damage sensitive electronic equipment and negatively impact the performance of electrical devices. Furthermore, grounding plays a crucial role in mitigating the effects of transient voltage surges, such as those caused by lightning strikes or switching events. While a grounding system alone cannot completely eliminate the risk of damage from these surges, it provides a path for the surge current to dissipate into the earth, thereby reducing the voltage stress on equipment connected to the system. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods or metal water pipes, connected to the electrical system's grounding conductor. The grounding conductor then connects to the service equipment, such as the main panel board, and to the neutral conductor at the service entrance. This connection between the neutral and grounding conductors is critical for establishing the low impedance fault current path. It's also important to understand the difference between grounding and bonding. Grounding refers to connecting the electrical system to the earth, while bonding refers to connecting non-current carrying metallic parts of the electrical system together to create an electrically conductive path. Bonding helps to ensure that all metallic parts are at the same potential, reducing the risk of electric shock if a fault occurs. Both grounding and bonding are essential components of a safe and reliable electrical system, and they work together to protect people and equipment from electrical hazards. Now let's delve deeper into the specific components and functions of a grounding system. The grounding electrode is a crucial part of the system as it provides the physical connection to the earth. Common types of grounding electrodes include ground rods, which are typically made of copper or copper-clad steel and driven into the ground, and metal water pipes, which can be used as grounding electrodes if they meet certain requirements. The National Electrical Code, or NEC, specifies the requirements for grounding electrodes, including their size, material, and insulation depth. The grounding electrode conductor, or GEC, connects the grounding electrode to the service equipment. The size of the GEC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. The GEC must be properly sized to ensure that it can safely carry the maximum fault current that may occur. The equipment grounding conductor, or EC, provides a low impedance path for fault current to return to the source from electrical equipment. The EGC can be a wire, a conduit, or other approved metal raceway. The size of the EGC is determined by the rating of the overcurrent protection device protecting the circuit, as specified in NEC Table 250.122. The EGC must be properly sized to ensure that it can safely carry the maximum fault current that may occur. The neutral conductor, also known as the grounded conductor, is the conductor that carries current back to the source under normal operating conditions. The neutral conductor is typically grounded at the service entrance, which means that it is connected to the grounding electrode system. This connection between the neutral and grounding conductors is critical for establishing the low impedance fault current path. When a ground fault occurs, current flows from the ungrounded conductor, also known as the hot wire, to ground. This fault current flows through the EGC back to the service equipment, and then through the GEC to the grounding electrode. The grounding electrode then dissipates the fault current into the earth. The circuit breaker trips when the fault current exceeds its rated value, interrupting the flow of current and clearing the fault. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electric shock. GFCIs work by monitoring the current flowing in the hot and neutral conductors of a circuit. If there is a difference in current between the hot and neutral conductors, it indicates that current is leaking to ground. The GFCI will trip and interrupt the flow of current if the leakage current exceeds a certain threshold, typically 5 mA. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a higher risk of electric shock. Arc fault circuit interrupters, or SIs, are devices that are designed to protect against fires caused by arcing faults. Arcing faults are dangerous electrical faults that can generate high temperatures and ignite nearby materials. SIs work by monitoring the current flowing in a circuit for the characteristics of an arc fault. If an arc fault is detected, the SI will trip and interrupt the flow of current, preventing a fire from starting. SIs are required in many locations, such as bedrooms and living rooms, where there is a high risk of arcing faults. Surge protective devices, or SPDs, are devices that are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, switching events, or other disturbances on the power grid. SPD work by diverting the surge current away from sensitive electrical equipment and into the grounding system. SPD are available in a variety of types and sizes, and they can be installed at the service entrance or at individual pieces of equipment. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. The grounding electrode and GEC should be inspected periodically for corrosion or damage. The connections between the grounding conductors and the equipment should be checked to ensure that they are tight and secure. The resistance of the grounding system should be measured to ensure that it is within acceptable limits. If any problems are found, they should be corrected immediately by a qualified electrician. In addition to the technical aspects of grounding, it is also important to consider the safety aspects. Always to energize electrical circuits before working on them. Use insulated tools and equipment. Wear appropriate personal protective equipment, such as gloves and safety glasses. Never work on electrical equipment in wet or damp conditions. If you are not comfortable working on electrical equipment, hire a qualified electrician. Grounding is a critical aspect of electrical safety and the reliable operation of electrical equipment. By understanding the principles of grounding and following the recommendations of the NEC, you can help to ensure that your electrical system is safe and reliable. The grounding system's effectiveness depends on several factors. Firstly, the soil resistivity plays a significant role. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is desirable, as it allows fault current to dissipate more easily into the earth. Soil resistivity varies depending on the type of soil, its moisture content, and its temperature. Secondly, the length and diameter of the grounding electrodes affect the grounding system's performance. Longer and larger diameter electrodes provide a greater surface area for contact with the soil, which reduces the resistance of the grounding system. Thirdly, the number of grounding electrodes also impacts the system's effectiveness. Multiple grounding electrodes, spaced appropriately, can lower the overall resistance of the grounding system compared to a single electrode. The NEC specifies the minimum requirements for the number and spacing of grounding electrodes. Fourthly, the quality of the connections within the grounding system is crucial. Loose or corroded connections can significantly increase the resistance of the grounding system, reducing its effectiveness. All connections should be made using approved methods and materials and should be inspected regularly for corrosion or damage. Fifthly, the presence of other underground metallic structures, such as water pipes or gas pipes, can affect the performance of the grounding system. These structures can provide alternative paths for fault current to flow, which can reduce the effectiveness of the grounding electrode system. It is important to ensure that these structures are properly bonded to the grounding system to minimize the risk of electric shock. In some cases, it may be necessary to use specialized grounding techniques to achieve the desired grounding performance. For example, in areas with high soil resistivity, it may be necessary to use ground-enhancing materials to improve the conductivity of the soil around the grounding electrodes. These materials can help to lower the resistance of the grounding system and improve its effectiveness. Another specialized grounding technique is the use of counterpoise conductors. Counterpoise conductors are buried wires that are connected to the grounding electrode system and extend outwards from the structure being protected. These conductors help to distribute fault current more evenly into the earth, which can improve the effectiveness of the grounding system. The design and installation of a grounding system should be performed by a qualified electrical engineer or electrician who is familiar with the NEC and other applicable standards. A thorough understanding of the site conditions and the electrical system is essential to ensure that the grounding system is properly designed and installed. Proper grounding is not only essential for safety, but also for the reliable operation of sensitive electronic equipment. Many electronic devices are susceptible to damage from voltage surges and other electrical disturbances. A properly designed and installed grounding system can help to protect these devices from damage and ensure their continued operation. In addition to protecting equipment, grounding can also improve the performance of electronic devices. A stable ground reference can reduce noise and interference in electronic circuits, which can improve the accuracy and reliability of measurements and communications. Grounding also plays a critical role in lightning protection systems. Lightning protection systems are designed to protect structures from damage caused by lightning strikes. These systems typically consist of air terminals, which are installed on the roof of the structure, down conductors, which connect the air terminals to the grounding system, and the grounding electrode system. The grounding system provides a path for the lightning current to flow into the earth, minimizing the risk of damage to the structure. The NEC specifies the requirements for lightning protection systems, including the size and spacing of the air terminals, down conductors, and grounding electrodes. The design and installation of a lightning protection system should be performed by a qualified lightning protection contractor who is familiar with the NEC and other applicable standards. It is important to note that grounding is not a substitute for other safety measures, such as proper wiring practices and the use of GFCIs and FCIs. Grounding is just one component of a comprehensive electrical safety program. All electrical work should be performed by qualified individuals who are familiar with the NEC and other applicable standards. Regular inspections and maintenance of the electrical system are essential to ensure its continued safety and reliability. If you have any questions or concerns about the grounding of your electrical system, consult with a qualified electrician. An electrician can inspect your system, identify any potential problems, and recommend appropriate solutions. Remember, electrical safety is everyone's responsibility. By taking the necessary precautions and following the recommendations of the NEC, you can help to protect yourself, your family, and your property from electrical hazards. The concepts discussed are fundamental to electrical engineering and safety. Grounding acts as a critical safeguard, ensuring that electrical systems operate safely and reliably by providing a low impedance path for fault currents and stabilizing voltage levels. Always consult with qualified professionals for specific applications and adhere to local electrical codes and regulations. In addition to the topics discussed, understanding the principles of electromagnetic compatibility, or EMC, is beneficial. EMC refers to the ability of electrical equipment to function properly in its intended electromagnetic environment without causing unacceptable interference to other equipment. Grounding plays a significant role in EMC by providing a low impedance path for unwanted electromagnetic noise to dissipate. Proper grounding techniques can help to reduce electromagnetic interference and improve the performance of electronic equipment. There are several different types of grounding techniques that can be used to improve EMC, such as single-point grounding, multi-point grounding, and hybrid grounding. The choice of grounding technique depends on the specific application and the characteristics of the electrical equipment. Another important aspect of grounding is the proper selection and installation of grounding conductors. Grounding conductors should be sized according to the NEC and should be made of a conductive material such as copper or aluminum. The grounding conductors should be installed in a manner that minimizes their impedance and inductance. This can be achieved by using short, straight conductors and by avoiding sharp bends or loops. Regular testing of the grounding system is essential to ensure its continued effectiveness. The resistance of the grounding system should be measured periodically to ensure that it is within acceptable limits. The connections between the grounding conductors and the equipment should be checked to ensure that they are tight and secure. Any problems that are found should be corrected immediately. Grounding is a complex and multifaceted topic, but it is essential for electrical safety and the reliable operation of electrical equipment. By understanding the principles of grounding and following the recommendations of the NEC, you can help to ensure that your electrical system is safe and reliable. And one last thing to add, the NEC also provides specific requirements for grounding different types of electrical systems, such as separately derived systems and high-impedance grounded systems. Separately derived systems are electrical systems that receive their power from a source other than the main utility service, such as generators or transformers. High-impedance grounded systems are electrical systems that use a high-impedance resistor to limit the ground fault current. The NEC provides specific requirements for grounding these types of systems to ensure that they are safe and reliable.